So to understand that a little bit better, let's look at the problem a little more carefully. I will just redraw the graph. As things stand right now, A can execute twice, but B and C are both stuck. What if I do one retiming step over here? Okay. So what do I mean by this retiming step? It basically means that I could, since the two edges, if you look at the two edges, one of them is going from the side of A to the side that B and C are on, the other edge is going from the side that B and C are on to the side that A is on. Okay. So I have to obviously adjust the way that I do the retiming. One thing I could do is -1 over here, +1 over here, right, which means that the resulting graph then looks like 1D over here and 1D over here. It was a very simple retiming step. How has this changed the way that I look at the problem? Now at t equal to 0, I can have A0, but I can also execute B0, right, and as soon as B0 is done, I can then move on to C0, which tells me that my iteration period is 40, and this is a blocked schedule. So you see what happened. What this is ultimately telling you is the data flow graph that you started with, if you just sort of blindly took that and then tried to execute it at the fastest way possible, eventually yes, it falls into a pattern that as long as you are willing to accept an overlapped schedule, will give you an average iteration period equal to the iteration period bound. Okay? That was the structure that we identified over there. But on the other hand, by doing a simple retiming step over here, I could convert it into a blocked schedule where I did not have to worry about whether two iterations were overlapping, whether I had to do two of them in the first place. I could just concentrate on one, right, and get the entire thing operating very compactly like this. Okay. Now from an implementation point of view, usually of course it ultimately depends on the kind of hardware that you are designing and how you would go about implementing it, but a block schedule is probably slightly easier to implement. Why? Because for executing any operation on a piece of hardware, you need to have some enable signal or some instruction, something that's going out to that piece of hardware saying, now you are going to execute this particular operation. If it's operation A, if it's function A, then there will be an enable signal that basically tells it, okay, operate in this manner, use this input, do this, compute this output. Okay. For a blocked schedule, I can just sort of have those enable signals and say, okay, from time 0 to 40, how should the enable signals be generated for processor 1 and processor 2? That's it, right? Whereas for an overlapped schedule, things are a little bit more tricky. I need to keep in mind that there are two different copies of execution going on. I need to keep track of all the time instants across that entire overlapping period and say, okay, these are the different changes that need to happen at different time points in time. Not impossible, of course, otherwise people would not even be considering overlapped schedules, but from an implementation point of view, it is likely that a block schedule is going to be a slight simplification, probably a slightly simpler way of achieving the same result. Okay. So what's the bottom line? Both of these data flow graphs, the retimed one as well as the original one, correspond to the same functionality that goes from the property of retiming itself. Okay. But the fact is, once you do that one retiming step, how you schedule it, what it converts to in terms of the sequence of operations that are executed can change. So how should I go about finding the best or optimal kind of retiming in order to do this? That itself is a subject of some study, but at the end of the day, it is not one of those things that you need to worry too much about, because if you think about what happened over here, we did not even really do anything fancy in order to come up with this overlapped schedule, right? We just pretty much started executing things as quickly as possible, allowed it to run for a little while, and we found that the entire thing falls into a pattern and we had to identify that pattern. If you are doing this manually, you can do it, that's probably how you would go about doing it. That does not scale a computer cannot go around just randomly executing things and looking for patterns. That is number one. The second is you might not find a pattern very easily, or you might find that the pattern gets too complicated. After all, over here there were only 3 operations to be executed. What if there are 20, right? And 20 is itself a fairly small number. Okay. So, the point is there are systematic procedures by which you can go about scheduling this. We will look at some of the scheduling techniques going forward, but why are we sort of looking at all these different methods in such a complicated fashion rather than just saying, okay, this is the problem to be solved, let us do it? Because it turns out that these problems are computationally very hard to solve. Okay. From the in the terminology of algorithms, right, computer algorithms, not DSP algorithms, they fall in the category of the so called NP hard optimization problems, which basically, to summarize quickly, essentially what it says is, it is very unlikely that you will find an efficient polynomial time algorithm in order to solve these problems ever, okay, in the most general case. All right. So, like I said, 2 things. One is the terminology, block schedule, overlap schedule, Gantt charts, as well as the fact that how would you go about finding such a schedule in such a case.